It's an age of civil war, as the Galactic Empire hunts down the Rebel Alliance across the galaxy. With their focus distracted, there is an opportunity for thieves and smugglers to make a living across the stars. Stealing the Trailblazer after a job gone wrong, Kay Vess escapes the Zerek Besh syndicate on Cantobite, carving out a name for herself on the Outer Rim, working with the Pike Syndicate, the Hutts, and the Crimson Dawn in an effort to curry favour while ensuring they're not aware of the damage she deals to each of their respective enterprises. As Vess hides out in the Toshal system, the real story that hides in plain sight is how artificial intelligence helps deliver the experience of high-speed chases on the plains of Toshara. I'm Tommy Thompson, this is AI in Games, and this is Star Wars Outlaws. Released in 2024 and developed by Massive Entertainment, players run a variety of missions across various planets in the Star Wars universe, be it the moon of Toshara, the dry and arid Tatooine, or the damp jungles of Akiva. In each case, you ride around on a speeder bike, a classic vehicle from the franchise that hovers above the ground and moves at high speed. While the non-player characters you meet in Star Wars Outlaws are built using traditional game AI, all of that changes when an NPC gets on a speeder bike. These vehicles need to navigate complex terrain, respond to in-game physics, and are often used to chase the player down in key sequences. As a result, they need a fast and effective solution to compute how and where to move in the heat of the moment. And as given away in the introduction, the solution was to adopt machine learning. Like its contemporaries, such as Electronic Arts and Activision, Ubisoft has an internal technology group that has a team of specialists that work to build tools and tech to support their game development teams, be it for game engines like Snowdrop or other bespoke toolchains. A part of said technology group is the machine learning team that works to provide a suite of tools that allows studios to use machine learning in ways that they see fit, and this led to a collaboration between the technology group and Massive to ship these ML-controlled speeders. As detailed in a GDC 2025 talk by Colin Gaudreau and Andreas, the team at Massive were excited about the prospect of adopting the ML tools built by the technology group. But given their previous games, notably Tom Clancy's The Division, which has no machine learning in it at all, they found themselves at an interesting crossroads of trying to figure out whether machine learning could be used to suit their design goals, having no experience with it. But ultimately, they found a good balance that enabled for it all to work as intended. So let's take a look at how it all came together. So, as stated, the team needed controllers for the speeders. This would handle both their movement in the open world as they simply drive down the road, or in chase sequences with the player as a result of encounters or specific story missions. While there were existing PID controllers within Ubisoft, proportional integral derivative controllers, which are common for controlling dynamic objects such as vehicles in games, the team were actually pretty confident in the ML solution being able to handle the faster-paced driving style necessary for Star Wars Outlaws. And so Outlaws uses an existing ML solution within Ubisoft known as SmartDrive, a machine learning controller designed for handling the movement of vehicles. SmartDrive uses reinforcement learning to train neural networks such that they can follow paths, adhere to speed limits imposed on them, and avoid both static and moving obstacles. And we'll discuss how that works in a second. SmartDrive has actually been a part of the technology group's machine learning framework for some years now, and has been showcased in a variety of demos during that time. Said framework is in essence a similar idea in principle to that of Unity's ML Agents toolkit, or Unreal Engine's Learning Agents API, where they interface game engines with a Python backend for training AI agents to solve specific tasks. If you would like to know more about Unreal Engine's learning agent tools, be sure to check out the talk by Brendan Mulcahy at the 2024 AI in Games conference. Though of course in this instance the ML framework is designed to work with Snowdrop, which is the engine used for the likes of The Division and Star Wars Outlaws, as well as Anvil, one of Ubisoft's other engines most recently used to ship Assassin's Creed Shadows. And it speaks to the maturity of the technology that when they dropped in an existing model, one that had been used to drive a regular car, and hooked that up to a speeder, they found that it already had a good chunk of the behaviour working from the get-go. So the next step was to figure out how best to adjust it, so that the model could be trained to handle the specific requirements set out by the game's designers. Okay, so how do you train a Star Wars speeder using machine learning? The model that controls the speeder is built using an artificial neural network. And of course, we've seen neural networks crop up in a variety of shapes and sizes over the years. As a reminder, a neural network is a non-linear data structure where we process input signals through data processing units referred to as neurons. You train these systems by modifying the weights between each neuron, which modifies the strength of the input signal as they move through the network from the input to the output layer. All of this reminds me we've still not done an AI 101 episode on neural networks. I should really look into that, but there is a video all about how machine learning, notably neural networks, are used in a variety of contexts across the games industry. But also back in 2024, we talked about the indie game Little Learning Machines that has you train neural networks using reinforcement learning to guide little NPCs to solve puzzles, akin to games like Creatures in Black and White. So yeah, go watch those if you're curious. Now, the network used in Outlaws is actually rather small, at least when compared to what we're talking about in contemporary AI. In fact, when compared to the generative AI models we talked about in episode 78 that are trying to simulate the behavior of entire video games, the speeder networks are minuscule. Generative networks to simulate games require billions of parameter weights, but this one only had tens of thousands to resolve. But as we'll see, even at this size, they're a really good fit for the problem they're trying to address, and the tech worked really well once they started to make some smart concessions. But yeah, the actual network, very small. It feeds in inputs from the game engine, and it passes it through two layers of 256 neurons each, and this is then passed into three output neurons. Two that handle the throttle and steering of the speeder, which are mapped as continuous values given they're mapped to the right trigger and the left stick on a controller, and the final neuron for the handbrake, which was a simple yes-no Boolean value. But how does the speeder then see the world that it can feed it into the network? Well, the devs break down the game world into two distinct elements: the immediate vicinity and the path the speeder is meant to be moving along. The paths themselves are computed courtesy of the navigation mesh built into the engine, and then it breaks it down into a corridor of triplets containing the left point, the center point, and the right point. Each of these triplets then exist on the path at fixed distances along the way. Meanwhile, nearby obstacles are recorded by breaking up the space around the speeder and finding if sensors intersect with a nav mesh edge that would line up with an obstacle. But of course, that only works for a static obstacle, because even if the nav mesh could capture moving objects, they'd be moving too quickly to wait for the nav mesh to update itself. So dynamic obstacles are tracked by their relative position to the speeder, though it can only track two at a time. But it's not just the environmental information. There's a lot of other data being fed into the network as well about the speeder itself, including the current forward, angular and drift velocity, the elevation angles, given the surfaces are seldom flat, but also the previous actions taken by the speeder over previous frames. This is super important, given if it's trying to make turns or fast movements, it's vital that it can retain context of what has happened previously, rather than forget what it was doing halfway around a turn. Now, the way this works is that the neural network gets in all of this input, processes the information, and then it generates the output. But when starting out, it's as smart as a bag of hammers. You next need to build the infrastructure for it to learn. Now, the bots are trained using a setup whereby the ML framework is running in Python separate from the game engine itself, whereby it sees how well it's performing and it feeds the information back to update the model. Now, the algorithm used for all of the ML fanatics out there is soft Actor Critic, which is a rather popular reinforcement learning algorithm for this kind of problem. Now, I won't go into detail how the algorithm works in the video, but I'll leave some resources in the description. But the key thing to understand is that it is assessing how well in every training segment, known as an episode, the agent succeeds at controlling the speeder in the scenario it is given. It then adjusts the weight of the neural network as it goes, so it can then try all over again. And over time, if things work as planned, it gives the illusion that the speeder is learning. So, speaking of, let's take a breather, do a nice Star Wars feathered wipe, and then dig into how training episodes and the environment are built in order for this to work as intended. Oh, there we go. That was a good feathered wipe, huh? Really Star Wars style too. Okay, so the setup we've discovered thus far means that there's a mechanism for feeding information to the neural network speeder, it can control the speeder, and there's an algorithm set up for improving the model. So now it's about setting up the problem so it's well scoped. By setting up the training environment and what's known as the reward function, it creates a situation that tells the agent what behaviour is desired without dictating exactly what the end result should look like. Now, this is one of the strengths of machine learning in practice, in that you can build up the problem around the AI agent and then leave it to figure out the answer. And critically, it's learning a general behaviour, or as we call it, a policy, to handle any path it could meet in the game. This makes it rather resilient to any changes made to the game map during development. But despite this, it can still be quite difficult to get the end result the way you want it. So let's start by discussing how the training environment was built, and then we get into the reward function and all those little problems that crop up that the dev team had to work around. One of the very first challenges faced is how to build a training environment for the speeders to run in, typically known as a gym. The development team originally created a fairly basic game environment like you see on screen now, in which the agents could spawn randomly on the map and then be fed a simple script telling them where to go, and then they figure it out along the way. Leaving the bots to train in this limited space, after only around 12 hours of training, was enough for them to figure out how to get around it successfully, and the final result, when deployed in engine, was good, if not great. What you see here is an example of a speeder bot they trained in just 12 hours on a single development machine, and already it's getting pretty decent output with little effort to tweak or adjust the machine learning algorithm and everything else. But it still needs a bit of work. One of the biggest issues is that you need to make sure it can handle all of the possible scenarios that will emerge in the open world. But it wasn't feasible for them to just have them training in the main open world maps of the game. To do that, you'd need to customize a lot of the back-end code in the game to create a essentially custom version of Star Wars Outlaws, where everything except the relevant scripts for training the ML bots was deactivated. Contrary to what people might say on the internet, that's a lot of work, effectively creating a unique copy of Star Wars Outlaws that only works for the ML bots. And this opens up all sorts of production risks, particularly when you're on a tight schedule for a game that needs to ship. So instead, they expanded the gym to include a lot more features you'd expect to see in the main game map, including the likes of road networks, narrow canyons, and even adding wildlife NPCs so they learn to dodge around them. Then, they worked to automate the whole process so it became easier for the external training codebase to interface with the game engine and run the training, with just a couple of button clicks. Plus, the process had to be conducted for each type of speeder that exists in the game world. So once a type of speeder was trained and ready to go, they would then continue to populate the gym with these pre-trained vehicles, so as to normalize the idea for the other speeders that you're going to be driving around them on the regular. Now, with the training environment in place, the second critical aspect is to properly define the rewards. When using a reinforcement learning algorithm, we need to define what is known as the reward function. This helps the AI speeder figure out what it's doing that is considered good versus what is bad or just simply undesirable. And that's how it learns over time to do what we want it to do. During training, the speeders are rewarded per step, which means every time point after they've taken an action, which is critically when it's going to act again, they are rewarded each step for 3 things. How far along the prescribed path have they reached? How well are they staying on the path, and how well are they matching a target speed set by the designers for that path? But given this is a reinforcement learning algorithm, there also needs to be punishment every time it does something wrong, thereby reinforcing good actions over bad ones. Hence, the speeder receives a penalty when it makes a collision with something else, but this is actually scaled between 0 and 1, and it's based on severity over time. So if it slightly clips something, that's fine in the grand scheme of things, but if it is grinding against another vehicle for several seconds, then that's really bad. So clearly Luke Skywalker never learned to ride an Imperial speeder using SmartDrive. It would consider the training episode to be completely successful if it actually reaches the end of the path, and it gets a big chunk of reward for doing so, thus incentivizing it to reach for the goal. But there's also a time limit on how long the episode is, and it receives a big penalty if it never reaches the end of the path. But also if the vehicle falls off the map, hasn't moved for a while, or simply hasn't moved along the track in any meaningful way, they then terminate the episode and denote it as a failure. This last one is critical, given, as we mentioned, the reward function gives credit when a bot continues to move down the track, but it could conceivably score a lot of reward by simply moving back and forth along the same segment of the track. So the success and failure of the episode has to factor in that the AI speeder might learn to cheat by exploiting a loophole in the scoring system. And as we'll see shortly, there were still weird behaviours that emerged because of these small loopholes that existed. So with this, it brings the bots much closer to their intended behaviour. They can stay on the road and generally perform a little more intelligently. But as you can see, there was still a bunch of issues in how it handled movement, plus a bunch of extra problems along the way. So I'm going to wrap it up by looking at all the weird edge cases that the dev team had to factor in. While I was researching this episode, the thing I really liked about the work that Massive did here is that they spent a lot of time evaluating the performance of these speeders, both quantitatively, meaning they checked how fast and efficient it was to calculate, but also qualitatively, meaning they're looking at how good the model is and then making tweaks to suit, be it in the model itself, how it was trained, or actually just overriding it entirely. Returning back to that clip from a minute ago, where the behaviour still had some issues with the throttle, it's also snaking around a lot and not staying consistent on the track. This was reduced somewhat by limiting the width of the corridors they followed, but also by modifying the reward function to say that they get slightly more reward if they stick to the centre of the path. While they don't overtly punish being off-centre, the small additional reward encourages them over time to snake on the track a lot less. But this actually resulted in another problem, in that because they now stay closer to the centre, the bot was learning to constantly wobble the steering column, something of a byproduct of the centering reward perhaps? So they altered the reward function again to now penalise the bot for large changes in the steering input between each time step, and that cuts it down quite drastically. But critically, the secret to getting the final bits of desirable behaviour is that there were specific edge cases where they simply turn off or override the SmartDrive controller, given it doesn't really allow them to do what the designers needed. Regular viewers may recall that this was something that the Forza Drivatars do as well, as we discussed way back in episode 60. So yeah, there are two distinct scenarios where they do this regularly. The first was for when a speeder needs to stop. The devs were actually struggling to get it to slow down and stop where intended. They would often overshoot their final destination. Not by a massive amount, but enough that as a developer you think, God, that's annoying. So the first phase of resolving this was to tune the inputs of the model so that it had a clearer indication of the desired target speed it should be going at relative to the distance to the target location, thus telling it to gradually ease on the throttle the closer it gets. This made a small improvement, but it still wasn't perfect. So to get over this, once the speeder gets within a radius of the destination, the AI controller simply ignores SmartDrive, and there is a handwritten controller that handles the braking more aggressively. The final issue was actually something that the bots weren't trained to do, and that's to crash. After all, they'd been told to behave intelligently, but the devs wanted to create scenarios where they would drive erratically and show them losing control before they blow up, because that's pretty cool. So they override and ignore SmartDrive to run a custom behaviour, like you see on screen now, that has it swerving everywhere until it blows up into a million pieces. As we move to wrap up this episode, the reason I like this machine learning project in Star Wars Outlaws was that as soon as I read about it, it just made perfect sense. It's exactly the kind of problem that machine learning is well suited for, and it's being deployed in ways that facilitate a very specific design goal without interfering with any of the other AI systems in the game. But also that we've reached a point of maturity where this kind of idea can not only be explored, but implemented quite efficiently. Naturally, I make it sound a lot easier than it was in reality, and we're still at a point where it's a challenge for ML toolsets and philosophies to be integrated into game development workflows. But in the past decade or so, the technology and the collective knowledge on how to make this work has reached a point where you can deploy ML for a specific part of your game, and it's just another aspect of the overall experience. I started my journey in AI for games over 20 years ago, training neural networks to solve control problems like this one, and to see something that is still, in many respects, similar to the work I was doing, but, done correctly, and shipped in a AAA title, well, I just think that's pretty cool. Note that this is but one example of how the ML framework team at Ubisoft have engaged with specific game studios. In fact, their work has been put to good use, both in the bots in the long-running live service melee combat game For Honor, and more recently in the highly popular Tom Clancy's Rainbow Six Siege. I've left some links to other talks and resources on its adoption, as well as the original talk this video is based on, by Gaudreau and Lassus. Critically, it was a really good presentation, and it also goes into a lot more detail on some of the other issues that they had that I don't cover, and the other broader production challenges. So if you found this interesting, be sure to go and check out the original source. Plus, of course, if you're a fan of massive entertainment, I've previously explored the AI of their games, with both a 2-part segment on the original Tom Clancy's The Division, followed by a 3-part series in collaboration with the studio, where I interviewed the AI lead of Tom Clancy's The Division 2, Philip Dunstan. And with that, it's time to start bringing this episode of AI in Games to a close. 80 episodes. Man, that's insane. How are we still here? How do I still have my voice? Well, I've lost my accent a little bit, I get enough pelters for that. How are some of you still watching this thing? How have we not made another alien isolation video yet? Well, yeah, more on that soon, I guess. But thank you so much for checking out this latest episode, whether this is your first time on the channel, or you've been a subscriber for many years. I appreciate you all, and I'm grateful you're still here to listen to me ramble on the internet. AI in Games is funded thanks to our wonderful audience, and you can help support the show over at aiingames.com, where you can sign up to our newsletter, catch new updates every week, and get early access and a whole bunch of other insider stuff by supporting the show. Check that out. I'm going to get back to work. Stay safe, take care, and I'll be back.